Greetings. I've owned quite a few breadboards in my time, but the ones I had were usually just a breadboard, like this part, mounted on a base plate with a couple of terminals to hook up power to them. They've been making breadboards with built-in power supplies for a long time, but I used to be either too poor or too cheap to buy one of those, so you would set up the breadboard and then you'd have to hook up power to it and all of that stuff. So finally I said, hey, now that I'm all grown up, maybe I can get myself a real breadboard like this one. And thanks to the generous donation of one of my Canadian viewers, this is now in my possession. It's an E&L Instruments C.A.D.E.T 2. It must be mid to late 70s. We can probably tell later if we look at the date codes on the chips and stuff inside. But it has a whole array of stuff on it, other than, of course, having a large breadboarding area, and then surrounded by a whole bunch of functions. Let's look at what it does. Starting up here, this is the DC supply section here, and we have binding posts labeled ground -V, which goes from 1.3 to 15 volts, plus V, which goes from 1.3 volts to 15 volts, and a fixed 5-volt supply over here. We have two pots over here that adjust the variable voltage feeds of the yellow and the blue binding post. We have another supply over here, which is basically the output of a center tap 12.6 volt transformer. We have a center tap and one each of the legs. The center tap I've checked, is not connected to the ground, so it leaves that up to you. Next, we have a function generator over here that allows you to select 3 waveforms: sine, triangle, and square. We have a frequency range selector. We have a fine tune for the frequency, which is graduated between 0.1 and 1.0, and an amplitude. We have outputs that are fixed TTL levels and variable levels, which you can adjust with the amplitude rotary over here. 2 debounced switches, which are normally closed, so it's not just a switch that'll bounce all over the place, but there are probably flip-flops in here to give you a nice sharp transition for every button press. A convenience here, which is a BNC jack, and really all that doesn't have any smarts. You just connect your wires to the tip, to the pin, and to the case, and that makes it convenient to hook up to other test instruments. We then have logic switches, which are most likely not debounced, but what you can do with them, they're 3-position switches. They can be, are they 3? No, they're 2-position switches. They're either 0 or 1, and you can select between TTL compatible voltage and the positive voltage, which you adjust up here. Then we have 2 pots, just 10K pots, that have 3 outputs brought out to these mini breadboards. We have single pole double throw switches over here, all terminals brought out to this breadboard. A speaker, I don't know if that's amplified or not. I would guess it's not, because we got the pots over here, so we probably use these as volume pot. We have two 7-segment displays which are driven by a BCD input. We have a logic probe. On the logic probe, again, the interesting part here is you can give it a VCC, but it's up to you. You can basically give it TTL, or you can give it an adjustable voltage depending on the level of your incoming signal. You have different modes, MEM and pulse. And then we have an 8-channel logic monitor, which is pretty much the same thing as this, except that it's got 8 LEDs. And yes, again, you can adjust whether the voltage is TTL standard or the adjustable positive supply. And that sums up what this unit offers. It came with this nonsensical circuit installed. I mean, it's hooked up to a few buttons. Then there's a 74HC16 over here, which is just quad inverters. And the wiring doesn't make any sense over here, so I'm suspecting they may have had a different chip in here. The wiring is then straight brought over. There's nothing else in here. And it feeds the 8-channel logic monitor and the 7-segment displays. And when I turn it on, and I'm not going to hook this up to an isolation transformer. I think we're good here, but I turn it on and nothing happens. So I guess I should plug it in. All right, try number 2. Turn it on. We get zeros on the LCD and some lows here, but as you can see, if I press on it, it changes the state of the LEDs. They start to oscillate. I think what happened here, this unit originally must have been very dirty, which means there's a lot of dirt and dust on the actual prototype breadboard, and the wires are just not connecting very well. I mean, this was cleaned up. It didn't come the usual in the usual filthy state I get things like. So my guess is that the seller may be female, because I've noticed that when you buy something from a female seller, they at least make an effort to not give you something that looks like it just got pulled out of the sewer, whereas generally you get something that wherever they bought it, whatever auction, they just pack it up with all the dirt and ship it to you. Nonetheless, it is still, as I said before, I think these are dirty. I'm going to try to clean them, but if I can't clean them, you can still buy these breadboards, 4 of which are on here, and then maybe replace them, but we'll get to that later. So before we get to the good part, let's see, out of the box, test a few things on it. And let's get started with the DC voltages. Just to scale to 2 volts. And starting with the 5-volt fixed DC supply. Scope tells us we're getting 5.04 volts. Well, that's good. Next, we have the adjustable positive DC voltage. If we turn that down all the way, we get 1.26 volts, and it's specified as 1.3 minimum. Probably need a little more scale here, so let's go up to 5 or 10 volts scale. Crank it all up. Well, And we end up with 21.6 volts, which is quite a bit higher than the specified 15 volts, but I guess the smoothing capacitors are working really well. On to the negative supply, set to minimum, tells us we're getting minus 1.12 volts, and cranking it up, we get minus 22.4 volts. Again, it's symmetrical, it's just as high as the positive, but it looks like the DC voltages are working. We then get to the transformer output, measuring it against the center tab, and we probably need to add a maximum here in channel 1 to measure the maximum, because otherwise it'll give us the mean, which is going to be 0, hopefully. So the maximum, measuring one of the legs, is 12 volts. Oh, so even though it's labeled as 12 volts AC from the blue to the red terminal, I guess each leg is 12 volts AC. So if we go to this, yes, we get another 12 volts right on the nose, and if we measure from each side of this, we should get 23.6, close enough to 24. So it's a little bit misleading the way they got this labeled, because it leads you to believe that each leg supplies, from outer leg to outer leg it gives you 12.6 volts, but it's actually from each leg to center it gives you 12 volts AC. But that also works. Next we'll look at the function generator. And we're just going to use the variable output for now. We got this set to sine wave. Yeah, it's a pretty decent looking sine wave if you get good contact. We're currently, coarse frequency is on 1K, and the fine frequency has a multiplication factor of 1.0, so we should be getting 1K, and we're getting 998 hertz. So that's pretty good. We go to the triangle, still maintaining the frequency and a pretty clean display, and to the square. So we're good here. So now let's go through the range. Let's go back to the sine and set the base frequency to 1 hertz. So as you can see, let's turn down the time base here. So here's our frequency. The scope can't measure it because the lower limit for frequency measurements is 10 hertz. It just says less than 10 hertz. But yeah, symmetry looks pretty good. Amplitude can be changed, or I should be able to change it, but it doesn't look like oh, there you go. Okay, so we can change the amplitude of it. So the absolute slowest is if I set the multiplication, the fine tune on it to 0.1, at which point well, this can't measure it, but what we're supposedly looking at is 0.1 hertz. So the next step is 10 hertz, and we can probably speed up a little bit. Oh yes, and of course we have the try and the pulse. Looks pretty close to a 50% duty cycle. You can't change the duty cycle. Next we crank this back up to a fine tune of 1.0 and go to a base frequency of 100 Hertz. And the scope says it's 99.235. I mean, I'm sure I could adjust this. Now it's pegged out. The fine adjust is pegged out. So I guess to get 100 Hertz, you got to go to the next base frequency. Let's go to a base frequency of 1K. And the scope says we are at 1.008 Hertz. Again, we can change amplitude and waveform, and that looks fine to me. We go to 10K, where we're beginning to get some garbage at the troughs and the valleys. I mean the peaks and the valleys. But let's see, the scope says 9.8 kilohertz. Still close, because we can always jump to the next range. Then we get to the max range of 100K, where that dirt in the peak and the troughs gets pretty pronounced. The frequency measured is 99.8 kilohertz. Amplitude is still adjustable. Doesn't have changing the amplitude doesn't have a whole lot of effect on the glitches over here. But yeah, that's it kind of passes. I mean, it may need new capacitors, and it definitely needs the pots to be cleaned. Then when we go to the TTL output, well, let's go something more reasonable, 10K. That'll always give you a square wave. You cannot adjust. You can adjust the amplitude. That's strange. Oh, we're not adjusting the amplitude. The signal must look pretty bad. That's why. But the funny thing here is it's telling us that we're running at 19.6 kilohertz, where we should be at 10. Maybe if I move the trigger up. Oh yeah, the trigger was just on baseline. So yeah, we're getting the proper frequency. We can change the frequency. And again, we cannot change the duty cycle, which would have been nice. But it kind of passes the function generator test. To test the rest of the stuff, I think we need to build a somewhat less nonsensical circuit in here, and of course clean it up as much as we can. I was thinking of squirting isopropyl into this hole, into all of the connection points over here, and then using compressed air that'll hopefully dislodge dirt and corrosion inside. Do that a couple of times, let it dry, and hopefully that'll clean up the connection points in here. But see, it's been on for a while, and these LEDs are all on. And, well, no, there. I was going to say they lost their sensitivity. Well, they lost, there you go. So here, and I don't know whether it's the wires that have corroded or the contacts, but we'll find out when we clean it. So here it is. I've removed all of the screws around the perimeter of the top board and disconnected a bunch of connections inside so that we can lift this off, hopefully. And there's what's in the case. Not a whole lot. The bottom's empty. That's about all there is. So that's basically the power supply section here. It's got a main transformer, board with a bunch of regulators on it, speaker, and the extra transformer, which I think is routed directly to the center tap transformer outputs on the panel. And I'll probably go in, check out some of the smoothing capacitors. Now, I was wrong about the date of this board. I said mid to late 70s. This PCB is clearly marked copyright 1990 behind this connector, these connectors. So it is a more modern thing than I thought. But yeah, let's look at the panel itself. Here's the panel itself flipped over. There's some connectors that go from the PCB to the actual panel itself. The panel itself is also made of a fiber board. And I think if we remove all of these nuts over here, the two will separate because these connections have been unplugged over here. And I think then we can see what's actually going on in here. Okay, we have one more nut left over here. Be careful not to lose the washers. They have, all the washers are there, which probably means that this has never been taken apart. However, it doesn't feel like this wants to separate, or maybe it does. See if I save those washers. I mean, I don't want to yank on it if it's still screwed together, which it probably is. Well, it is moving. All right, I think what's holding it in is the pots and the selector for the function generator. So I'll probably have to remove the nuts holding these to the front panel. Sorry it took so long, but the knobs had these tiny Torx set screws on them, two of them, and they were tightened pretty nasty. It was difficult to get them out, and I wanted to be very careful to make sure, you know, not to wear out the screws. I finally did get them out, but took a little longer. And the funny thing is these two shafts are D shafts, which means, you know, the outline or the cross section is shaped like a D, and those don't really need knobs with set screws. I mean, they'll just have a knob that has a D spline in it, but I guess these two need those, so somebody said, yeah, let's just put these guys in here and fasten the set screws to a plastic shaft, which is never a good idea, but anyway, that's what it is. They're out, and we should be able to get the PCB out now. And here we go. Come on. There you have it. So this is the back side of the front of the top with the breadboards and stuff on it. Few pots. I will now be able to get to these pots to give them a nice spray of contact cleaner. But of course what you want to see is the board itself, and that's here. There's not a whole lot on it. And if we look at this closely, yes, it's got an 8038 function generator over here, and that's what generates that's what basically generates the clocks and the different waveforms. And the rest of it, a bunch of op amps, some CDs, and some CMOS stuff, probably to buffer signals that are going to the display. The LEDs are driven by, what are those? Those are LM339 op amps used as drivers, and other assorted bits and bobs. And that's about it. I mean, there's nothing very complicated in here. So yeah, there you have it. I mean, the only purpose for opening this is to squirt everything with contact cleaner, deox it, and work all of the controls, make sure they're clean, and then we'll just put it all back together again. It's all put back together again, no parts left over, so everything's back where it belongs. The only thing I had to do was replace the rusty screws that hold the panel to the bottom of the case, and other than that, all we need now is to put something in here that's not as nonsensical as this circuit and see it do something. So what I did was I removed most of the old circuit, basically everything to the left of here is disabled. So from here on over here, most of the stuff's disabled. And what we're going to use is a decade counter, a TTL decade counter, a 74LS90 over here. And what that's going to do is count from 0 to 9 and then reset back to 0 and do that forever. Decade. 10. And it's wired up. The outputs are essentially BCD, binary coded decimal, and I'm using those to drive both the 8-channel logic monitor over here as well as one of the 7-segment displays here. What this chip of course needs is some sort of a clock, so I got it hooked up to the function generator, and the function generator is running, well, let's make it run a little faster. Well, no, we can leave it at 1 Hertz, which means we should essentially, when we turn this thing on, see it count seconds on the left digit, but it's going to start at a random place because there is no reset circuitry hooked up for this counter. So it will always start in a somewhat random fashion, but once it counts up to 9 and then resets, everything goes to normal. And for the purposes of this demo, we don't really need to worry about resetting this. So when I turn it on, the clock's going to start running at 1 Hertz, and we should see the seconds count down here, and we should see the BCD up here. So here we go. So as you can see, that's exactly what's happening here. Now the accuracy, of course, is based on how accurate these knobs are, which is not very accurate. But as you can see, it's doing its job. It's getting clocked every second, advances the count, and gets display over here. Now one thing I noticed that they did weird is basically the way this is wired up. The order of the bits had me confused. I couldn't get this to work for a while, but till I figured out that this is bit 0, bit 1, bit 2, and bit 3, and it's a logic monitor, so it doesn't just have So it's not just LED on off, but it shows high, low, and if we have a floating input, neither of the LEDs for that channel will be lit. But as you can see, it's happily counting seconds. Now, of course, we can multiply the counter by a factor of 10, and we will get 10 times as fast, and there you go. And then, of course, the faster we go, eventually the eye won't even see it anymore. Everything will appear lit. You can see a flicker there. But eventually, it looks like everything is on all the time. That's because the frequency is too high. Even though the frequency is only 1 kilohertz, the eye gets fooled into thinking that everything's on all the time. And that is a principle used a lot in SCAN. When you scan arrays of LEDs and stuff like that, you turn them on only a small percentage of the entire cycle. But if the update frequency is high enough, they appear to the eye as being on all the time, which we can witness here in the logic monitor. We can see that both LEDs are on. So if we go back down to the 10 Hertz here, then we can see it work perfectly. And if we go down to 1 Hertz, then it's counting seconds. And really the only other thing we can test here right now is, instead of having this clocked by a function generator, we can use one of these debounced push buttons over here. So this is the clock connection, which I'm going to remove and basically put into the first debounce switch, if the wire wants to go in, of course, which it doesn't want to. I gave it a little bit of a cleaning. I used some isopropyl on all of the contact points, and it's a lot better. I don't see flickering that much, but anyway, so we can test the debounce switch. How do I do this? Okay, like this. So every time we press it, the counter will advance 1 count, and of course, since it's on 9 right now, it'll go to 0. And it doesn't care how long I keep the button pressed, how quickly I press it. The button will always return a single clock pulse. Other than that, the other things in here, there's switches, which we can use the logic switches and the SP, the single pole double throw switches over here to basically display any number we want over here. But this gives you a very good example of some rudimentary use of something like this. You can basically stick in most TTL chips in here and simulate circuit operation and check them for proper operation by giving them either a clock, doing it via push buttons, permanent levels, or whatever. One of the downsides I have to point out is because these displays are wired, there's BCD to 7-segment decoders driving these. And what that means is you don't have control over the individual segments here. You give it a binary number between 0 and 9, and it'll display it properly. Anything outside of that range will make this thing go blank. So you can't play little games where you have the segments wandering around and animating this and all that sort of stuff. Because, this begs the question, if you remember the Heath 6800 trainer we had, I was kind of wondering if we could actually fit that entire trainer, all of the components, onto these 4 breadboards and have the trainer running off of here. But one of the first problems is, of course, first of all, there aren't enough digits here, and second of all, you can't control them segment by segment, which the trainer lets you do. But I'm sure we can come up with lots of other interesting things to use this for. And if you have any suggestions, don't be shy about commenting about it. Thanks for watching. Please like, subscribe, share, hit the bell, and all that other good stuff. And we'll see you next time. And I almost forgot. Can this thing make sound? Does have a speaker, does have a function generator, so the answer should be yes. So anyway, the speaker, one terminal gets hooked up to the output of the function generator and the other end to ground. Function generator is set up for 1 Hz square wave with the amplitude cranked. So go. So yeah, it can double as a metronome. It's running at 1 Hz right now, even though the astute observer may notice that it's actually popping twice a second. And the reason for that is every time the signal goes from either low to high or high to low, you will hear a pop coming out of the speaker. And in a 1 Hz signal, the signal will have a rising edge and a falling edge, and that's why it's running twice as fast as you would normally expect it to. But now, of course, we can start cranking the frequency. So we'll go from the 1 Hz range to the 10 Hz range, and to the 1K range. Or another interesting thing, of course, is going back to the 10 Hz range and putting the multiplier to 0.1. We can use the amplitude button to change the volume, go to the next highest frequency, put the multiplier down again, so yes, it makes noise too.